need a hug.
It's kind of really gotta be.
It sounds like it. It looks like it. Hey. Oh, you could turn it out, and I just got a new one.
Okay.
So it's something.
It was one packet?
Correct. It was, number,
I
it's the
tried
fourth
pulling
one.
it out before I got here, but my printer wasn't working, so I was.
Yeah, gotcha. Happens to me all the time. Thank you, sir.
Thank you.
Holding these hostage for no good reason. Somewhere.
Someone.
Yeah. Thank you, sir.
I thought it was in there, but I wasn't sure.
I'm hiding them all. Thank you, ma'am. I'll save it for, oh, it's already stapled.
Right there. I wanted everything.
Doesn't really matter that much. Actually, I already did it. Oh, that's not you, I'm sorry. I completely forgot that you took that, so I would have traded it for you. So,
Oh,
sorry
yeah.
about that.
Thank you.
I noticed that there was some integration by part at the top there. When you took the picture. Right. Oh, yeah, yeah, yeah. All that fun calculation. Suffering. Yeah. The two worst courses I took as an undergrad was Calc 2 and operating systems. Operating systems was the worst. The teacher I had, the other teachers called her the Dragon Lady. So it's kind of bad when the other teachers called with other teacher names.
What was your undergrad focus?
Computer science.
And operating systems was horrible?
Yeah.
Is it normally horrible, or is it just your teacher?
It was the teacher. First class, 100 PowerPoint slides. Deadly serious. 50-minute class. I said, I'm not good at math, but that's basically a little bit more than one slide per minute. And she's like, you're right. And then she just kept on going.
That's how computer science is.
Yeah. It's like, why even bother? You're not gonna learn anything, like looking at a slide for 50-some seconds. Oh, well. Almost need it. You're wrong. I know, I think I'm part of the day.
No, you just felt like.
I'm tired of doing
I'm thinking, you don't.
You got that new press.
Yeah. Well, there's a play in me.
Yeah, someone keeps moving through different
Not
places.
this play.
It would have
Donnie, I
been.
just said I was gonna take that. Walk it up. I'll staple it for you.
Thank you. There are two of them.
Extra. Sharon can have it. I did that on purpose.
Really?
Absolutely. Pass that back to Andre. Andre will pass that back to Rob. There we go. It's an efficient algorithm.
Coordination.
Check that out.
On the computer, you how to like do that, but just skip through all the numbers, just
Can't just go in linear fashion.
doesn't work.
No.
Kind of, I don't know, right?
I was about to say you could access from an array that way.
But that would take several lines of code, you can't just like tell it to do that.
Nah, it's not smart enough to do all that stuff. Okay, so we will press on with direct proof. Sounds like fun, right, guys? Thanks, Ryan, just something else. All right, so we're gonna take a look today at quotient remainder theorem, which is gonna lead us into the idea of being able to do proofs by division into cases, okay? And then after we start looking at some of that stuff, we'll start looking at maybe some of the floor and ceiling stuff, okay? So, we're looking at our next assignment. So, assignment number 5. That's gonna be due on Monday, what's that, the 10th? I guess so, today's the 3rd. Okay. So, if you guys have questions while you guys are looking through that, make sure you email me so that way I can answer those questions for you guys. Okay? All right, did I miss anybody with the packet, or everybody got a copy of this? Good enough. Okay. So I want to start with something called the quotient remainder theorem. Okay, that's going to lead us into being able to do the division into cases. The quotient remainder theorem says that if there's 4 integers, n, d, q, and r, all right, there exists a unique q and r, so that if I defined an n and a d, you could write that integer n in this form, dq plus r. So basically, we would have to find what the value of d is and what the value of n is, or sorry, the value of q and what the value of r is, to be able to satisfy this quotient remainder theorem. Okay, so I'm going to give you guys some of the stuff for this, and we're going to be able to do it. Okay, they're just number trick problems, they're not difficult. And then we're going to see where we would ever use this sort of thing in real life. Okay, not that any of us would ever use this in real life, but we can pretend. Okay, so the first thing I have is that I give you that n is 31 and d is 5. Okay, and we have to go under the assumption that there exists an r and there exists a q, such that this should actually be q here, guys, not d. Or I'm sorry, no, that's correct. So there has to be any value q, and it has to satisfy the d for this. Okay, so 31 is equal to 5 times q plus r. Okay, so that's what we're given. And basically what we have to do is we have to find a value of q and a value of r, such that r is between 0 and 5 in this case. Okay, it could be 0, but it can't be 5. So does somebody think they might know the values of q and r that would satisfy the quotient remainder theorem? It should be pretty easy. So it's
Q could be 6 and R could be 1.
in fact, that's the only pair it could be. Very nice. Okay? The only way that this could be satisfied is 6 and 1. Okay? Now, how come we can't use something like 5 and 6? Because we know that 5 times 5 is 25, plus 6 would be 31. So why couldn't we use 5 and 6 for q and r respectively? Go ahead.
6 is bigger than all.
Right, because we can't have an r that's bigger than the d remainder there. Very good, Don. Okay?
So do you have to do all the time like trial and error in this thing?
Well, basically trial and error is going to be the easiest way to do it, okay? What I always think of is like a div and mod, and think so that your modulus is going to be between d and r. Or I'm sorry, 0 and d. That's probably the easiest way to do it, okay? So just think of your multiplication tables to do it that way. Okay? Like for instance for b, okay, we know that 109 is equal to 13 times some number plus r. So once again, we just have to define what q and r are. Okay? So what you might want to do is just do 109 divided by 13 and figure out what the remainder is. So that way you don't have to do too much work with it.
Okay.
Okay? So guys, does anybody think they might know what q and r are respectively for this one?
So Q is 8.
Okay? So q would be 8, because 13 times 8 is going to be 104. And that would have to mean that r is what, guys?
5.
It has to be 5, right? So probably the easiest way to do these problems is to just take 109 divided by whatever d is, and then just say, okay, well, how many more do I need to get to 109 in this case? Okay, so that's all there is to it, guys. It's not difficult, okay? So does that help maybe, Art, with that, like, eliminating a trial and error method?
Yeah.
Okay. For this last one, we have negative 79 is equal to 8q plus r. Okay, now, typically this is what I'll see that's not correct. Okay, so I'll see that q is negative, oh, I'm sorry, I'll see something like this, I apologize. I think I just wrote the answer on the board, which wouldn't be good, so. But typically I'll see something like this, where somebody might write something like -9, and then they might put in something like 9 or something like that, okay, or 7, sorry. Sorry, -9, 10. No. Anyway. I keep trying, now I'm thinking of the wrong answers, and I can't think of the wrong answers, all I can do is think of the right answer. Sorry, not that it's a bad thing, because I guess you want your teacher to know the right answer. Alright, but with these types of negatives, what you want to make sure of is that you just go over a little bit, because remember, R has to be bigger than 0, okay? Like typically what I might see, now I'm thinking about it, I might see something like this, -9, and then -7. Okay, that's what I was thinking of. That's the one that I always see students do. And unfortunately, you can't do that because R has to be bigger than 0. Okay, so don't do that. I probably just confused you guys. Yeah, I probably just confused you guys by thinking of wrong answers. So for this time, it has to be -10 and 1 would be the right answer for this, okay? So with negative numbers, just go a little bit over and then think of your R to add it back into that, okay? So does that make sense, guys? Any questions about that? Not meant to be too difficult. Okay. One of the things that the quotient remainder theorem allows us to do is that sometimes, especially in computer science, we have to try to write numbers in specific forms. Okay, I'll show you guys an example of what I mean later. But if I give you guys a specific value for D, okay, there's only a finite number of cases that satisfy the given conditions. Okay, so I say use the quotient remainder theorem defined by n equals dqr, list all the possible cases. Okay, so if D is equal to 3, okay, I think that there's only 3 possible cases that we could construct that would satisfy the quotient remainder theorem. Okay, so does anybody think they might know what the 3 possible cases might be for this? So R would have to be 0, okay? Because remember, we said that R has to be, what do we say, 0 less than or equal to R less than D, correct? So that would be 3 times Q plus 0, right guys? That's one of the cases. Does that make sense, guys? Because R is dependent upon the value of D. What's another possible case? Yep, 3Q plus 1, good. And then the final case would be 3Q plus 2, right guys? We can't have 3Q plus 3, how come?
Because it's less than D.
Yeah, we have to make it less than D. We have to make R less than D, not less than or equal to. Okay, so when I say list out all the possible cases, if D were to be 3, these would be the 3 possible forms of the quotient remainder theorem. Okay, and like I said, later in today, I'll show you guys why you might want to know something like that. Okay, so knowing that, we might be able to write letter B. Okay, so does somebody think they might know what the possible cases might be if D were to be equal to 5 in this instance? Or maybe not.
5Q plus 0.
Okay, so N would be equal to 5Q plus 0, good. And then, John, you want to go ahead and do the other ones?
1,
Uh-huh.
5Q plus 2, 5Q plus 3, 5Q plus 4.
Okay. Sorry, I can't write as fast as you speak. Not that anyone can read it anyway. Okay. So basically, guys, whatever D is, that's how many possible cases there are. Okay? Now, I'm not asking you guys to find a specific number. I'm just saying write out the possible outcomes for this. Okay? And like I said, later today when we do a problem that involves quotient remainder theorem, the first thing you guys have to know is how many possible cases there are for the outcomes. Okay? So does this make sense, guys? Basically, whatever D is, that's how many cases there are, and you start at 0 and you go up to that number, but don't include that number. Okay? So for instance, if I said 2, you would just have 2Q plus 0, 2Q plus 1. Okay? Or in other words, even and odd, right guys? Because that's the definition of what, if D were equal to 2. Alright. In fact, we're going to do that a little bit today. Okay, so one of the most useful methods of proof is sometimes that if you don't necessarily have a definition for something that's nice, sometimes you can exhaust all the possible cases. Okay, So division into cases is one of the most useful ways to provide, or to prove universal statements, okay, if you can't utilize a definition. Like for instance, if I just say for all integers, okay? Well, that's kind of difficult because we don't necessarily have a definition for integers. But isn't it true that all integers are either even or odd, right? They're either positive, negative, or zero. So we might be able to use that division into cases, okay? Just an example of where you guys have probably used division into cases, but you don't remember it, okay? In Calc 1, okay? You don't have to copy this down, by the way, but how many of you guys remember this animal, the intermediate value theorem, okay? If you don't, just shake your head and lie to me that you did, that's fine, but, and you guys, yeah, that's right, good lie, Greg, I appreciate
F
that.
of b minus f of a by divided by b of a, that,
Not quite, okay? If I have a function, you're on the right track, but the intermediate value theorem says if I have a function, okay, a continuous function, all right? And we're not going to prove this, by the way. But let's say that you have a point f at a, which is less than 0, and this is point A. And you have a point B, and f at b is bigger than 0. Okay? What does the intermediate value theorem guarantee?
there is a point between a and, in the middle that's between a and b, right?
There's a point in the middle that specifically does what?
Equals 0.
Is a
Equals
0 in a
zero.
function.